But I think we should start anyway. It's a few minutes past 10. So it is a great pleasure to introduce Milton Lopes Filho, who's visiting us from Rio de Janeiro right now. And he is, to anybody working in mathematical fluid dynamics, I think a very well-known figure, having done a lot of work on especially 2D flow and vortex dynamics and PDE theory associated to these areas. And I think we are all looking forward to hear what he has to tell us on the wave vortex system.
Thank you, Marcel. Thank you. It's a pleasure to be here and give this talk to you. So let me. So the story I want to tell is this vortex wave system. It's one of those things in PD that has a very confined history. There's maybe at this stage 3 or 4 papers written on the subject, so it makes it easy to give you a complete story, and that's my intent. So just to tell you where it came from, and exactly what we know about it and what we don't. This is the body of research I'm reporting on. Has been done in collaboration, different parts of it with different groups of people, but it's all been done with these 4 people: Gianluca Crippa, Evelyn Mio from Paris, Eleonora Mora from my institution, and Helena Lopes, who's sitting here. So the basic context is 2D incompressible fluid dynamics, the ideal flow. The basic equation that I want to talk about, the basic model that I want to talk about, the vorticity equation. And from the point of view of this talk, I'm just going to concentrate on the full plane case, just because it makes it easier. And so I'm talking about the vorticity equation, omega t plus u dot grad omega equals 0, as an active scalar equation generated by the vorticity to the Biot-Savart law. And here's the explicit form using the notation perp for AB perp is minus BA. And K, I'll denote the Biot-Savart kernel by K, which will C perp over mod C squared, the vector Biot-Savart kernel. Just again to fix the background that we're working on. For this system, we have existence and uniqueness of a weak solution. If you start with the initial vorticity in L infinity intersect L1, of course, this is not the best result, but it's in some sense the baseline result. Everything that's known beyond this is very close to this in a sense for existence and uniqueness. And talking about, so I will call this the vortex dynamics model. And that's what people usually refer to. And some special cases of the vortex dynamics model that we're interested in for this talk are the contour dynamics particular region, where the equation models the dynamics of a region with constant vorticity. Of course, given the transport nature of this equation, if I start initial data with which is just a characteristic set, the characteristic function of a fixed set, this equation just gives you some kind of evolution for that set, and this is called contour dynamics historically. And another special example is the point vortex dynamics approximation, where you assume the initial vorticity is the sum of Dirac's, and these MIs are the masses of these Dirac's, and they start at initial point pi. And given such a distribution of vorticity, the Biot-Savart law associates naturally some kind of velocity field, which I'll call U is mi times k, the Biot-Savart kernel, evaluated at x minus pi. And vortex dynamics, the classical vortex dynamics, the Hamiltonian system is the point vortex system, the dynamics of these points, ignoring self-induced velocity. If you just put pi here, you're going to get k0, and k0 is infinity. So you just throw that away and look at the dynamics of a point as the dynamic evolving it through the velocity generated by the other points. That's the j different from I here. And this gives you a Hamiltonian system called the point vortex system, which is a classical model for a great many things. Yes?
The point vortex dynamics does not fit into the Udovich theorem.
No. And well, it's an ODE, therefore it fits into the into classical ODE theory. Okay? It's just another singular flow example that I want to focus on for this talk. Okay? And so the point was, the issue was, the basic issue is, you want to bring in, use this equation for flows which are more singular than just bounded vorticities. And one example being the point vortex system. So you'd like to get a framework where you could put in any measure here as initial data and let it evolve by using this equation. And unfortunately, the equation is not, I mean, this is not regular enough to do it. And there's been attempts to do it. I'll talk about it a little bit later. But after giving up sort of treating the whole point vortex or a general measure as initial data for that equation, Marchiori and Pulvirenti suggested something a little easier. And so let me assume the vorticity is given by something that's bounded plus some point vortices. And for simplicity, I'm going to take just a single point vortex plus a bounded part. And you couple the vorticity equation with the point vortex system in this precise way. And they call this set of equations the vortex-wave system. So precisely what it is that I'm doing, I'm evolving the point P by the velocity induced, so I have a continuous distribution of vorticity that I'm going to call omega naught, given initially, and a point vortex that I'm putting initially at a position P naught. I'm going to evolve the point vortex by the velocity induced by the continuous vorticity omega. And so the velocity at time t is the Biot-Savart kernel applied to the vorticity omega, where omega is the evolution of this omega naught. I'm going to evolve the continuous vorticity omega by the velocity that's induced both by itself and by the point vortex age. So age is the velocity induced by the point vortex, now depends on time. And then I put these two things here and I evolve the vorticity using the combined velocity by itself and the point vortex velocity. Now, of course, the point vortex is only being evolved by U because I'm throwing away the self-induced velocity in the same way that I did for the point vortex system. Okay? So Marchiori and Pulvirenti called this particular combination of the... So this is just a vorticity equation written differently in some sense. Okay? But separating the ODE part, the point vortices part, makes it, let's say, a little more amenable to analytical treatment. That's what I'm going to tell you about. What can you say about this system? It's a fair question to ask why they call it vortex wave. And I can only say that I haven't asked them. I'm planning to. But the issue, I guess that this is like particle wave duality in quantum mechanics that's inspired on that. So the P, the point vortex, is the particle, and the omega is the wave, in some very broad sense. But as I said, I owe asking one of them why they called it this. There's no waves in the story, basically. Okay. So measures as weak solutions. So the first issue is, why don't I do just the straight vorticity equation with a measure as initial data? So if I give the best result that I have for existence of such objects is if I give it an initial measure which is non-negative and compactly supported in H-1, I have the existence of a weak solution. It's a theorem by now, a classical theorem by Jean-Marc Delors in 1991. And of course, the problem here is that the Diracs are not in H-1 because the velocity induced by point vortices is not L2. So velocity is in L2, take one derivative, vorticity should be in H-1. And it's an easy calculation that the velocity induced by a point vortex is not L2 log, which means, well, you're out of luck if you want to include point vortices in this framework. In fact, it's rather complicated to make sense of Biot-Savart dot grad Dirac or Biot-Savart dot grad Biot-Savart in weak sense, although this one is actually easier to play with than K dot grad delta. Concentrations of vorticity, so the whole framework of Delors is precisely shown, the existence is shown by showing that if you start with something in this class here, Bm plus compact support intersect H minus 1, there is no concentrations of vorticity. You create an approximate solution sequence, and you send the approximating parameter to 0, and you prove that in this case, the vorticity cannot concentrate at points. So exactly, and this is what is needed to show that the nonlinearity for the equation is actually weakly continuous. So, and then you pass to the limit, you get a weak solution. So the basic idea behind Delors' proof essentially excludes Dirac's, even at the level of uniform estimates. Okay. Now, later, Frédéric Poupeau tried to do, he has a nice paper in trying to, very hard to include point vortices in this framework, but his basic idea called, leads to something called diagonal defect measures. Basically, the nonlinearity has a defect, and you end up with a limit that's not really a solution of Euler in any sense. So if you do approximations involving Dirac. So it doesn't seem like, although this is not definitive, it doesn't look like you can actually push the Delors framework or the weak solution framework all the way to point vortices. Okay? So the key to the point vortex system, of course, is ignoring the self-induced velocity. And this is kind of hard to justify rigorously. Basically, what you're saying is the point vortex is a model for a very concentrated bit of vorticity on a small near a point, on a set of small measured near a point. And the question is, if you're doing an approximation, say by Navier-Stokes, who's to say that this bit of vorticity stays concentrated or doesn't trade vorticity with the background? So who's to say the mass stays constant? Okay, and this is the key issue behind the point vortex system. So the point is that of course, the self-induced velocity is just rotating around crazily. If you add in a background, this tends to sort of spoil things enough that maybe that coherence is not maintained. And if coherence is lost, then this is the whole issue. It's hard to, that's the point, it's hard to justify just ignoring self-induced velocity in approximations. Now, one nice way, there are ways of justifying it partially. And one nice paper that does it to some extent is Vortices and Localization Alphas, an old paper by Marco and Pugliarenti, where they show that for a long time, and here a long finite time, the coherence is maintained, so point vortices behave like point vortices, although you can't say that for all time. Now, so now, back to the vortex-wave system itself. The whole story begins with Marchioro and Pugliarenti. They introduced the terminology in the system in '91, a paper on a conference proceeding. So, and they introduced the system and proved the theorem. It's a nice baseline result for us to start discussing. Now, if you start with some initial vortices with null infinity compact support, then there exists a globally defined solution of the vortex-wave system with one point vortex P. Okay. If the initial point vortex is not in the support of vorticity, then the solution is unique. So in this sense, you're picking up Udovic's theorem, and you're adding a point vortex outside of the support of vorticity. Okay, and then you get existence and uniqueness of a weak solution to the vortex wave system. Okay, so now the essential issue. So how do you do this? You have to follow Udovic's proof and make sure that the point vortex doesn't bother you. And, I'm sorry, make sure that the point vortex doesn't bother you. And the way to do that is to show that the point vortex never, if you start with the point vortex far away from the support of vorticity, you have to show that the point vortex never reaches it, okay, over finite time intervals. This is reasonable because the background flow is reasonably smooth, except for the point vortex itself, and therefore, you know, particle trajectories don't want to meet each other. So if you start outside of the support, in principle, you can't never get close to it. Of course, the whole difficulty is the velocity. There is infinite velocities involved, so you have to worry about what's happening to the point vortex. But anyway, so they can do it. Use the log Lipschitz regularity of the velocity, which is used also in the Udovic's proof, and show that the point vortex and the support of vorticity never meet. So you can actually manage to extend Udovic's theorem to prove this theorem by Marchioro Pulvirenti. Now, they themselves said, you know, we are doing this here assuming the initial point vortex is not in the support of vorticity, but you can probably do it if the initial vorticity is constant near the initial point, so that you stay in the constant, in the place where the vorticity is constant forever. And so they conjectured it, and very soon, this was proved, if you assume the initial vorticity is Lipschitz by Starovoitov, that was 94. And then for 15 years, these two papers, Marchioro Pulvirenti in 91 and Starovoitov 94, were the whole literature on the vortex wave system, until fairly recently, Lacave extended the result. Actually, I would say extended the result of Starovoitov, but it's really a completely different game. They actually proved the basic conjecture that Marchioro and Pulvirenti had done. They proved that if omega naught is bounded, and if you put P naught in a region where the omega naught is constant, then there exists a unique solution for all time. Okay? So my part of what I want to do is to look at this result by Lacave and other things that we started doing after that. Now, the first thing we did when we got into the story is this result. So we have Lacave existence and uniqueness for vorticity in L infinity and the point vortex outside of the support. And what we wanted to do is start pushing the regularity of the background flow further down, see how far we could go. And the first result we managed to prove is, and this is joint with Evelyn Mio and Helena Lopes, by now 2011, it's already published. If you assume the initial vortices in LPP greater than 2, then there exists a globally defined solution, weak solution of the vortex wave system. This doesn't, I don't need to, for existence, I don't need to assume that the point vortex is in a region where the vortex is constant. I always have existence. The whole problem is uniqueness there. And this is very natural. P greater than 2 is a very natural assumption here, because vorticity in LPP greater than 2 is exactly what I need to make velocity continuous by Sobolev embedding. And velocity is continuous means the point vortex is at least you have existence of a trajectory by Peano's theorem. So it's the right regularity to begin playing with this story. So this is a very natural assumption. The whole interesting game now is trying to get it below that, but say that would be a very natural guess to assume that this would be the right place to start. Now, to be able to play with this game, I need talk about notions of weak solutions, and we do introduce two notions, Lagrangian and Eulerian solutions, and playing around with these two notions is part of this game. So, let me just make one remark about this theorem. We actually formulated for any number of point vortices. The existence is global for one point vortex, or for several point vortices with the same sign. But we only prove existence up to vortex collision if point vortices are allowed to change sign. The point is that we can avoid, we can prove the point vortices don't collide if they're all the same sign. And this is sort of an energy consideration, sort of the conservation of the Hamiltonian implies that. But if you have point vortices with change sign, it's known that you can get collisions even if you don't have a background vorticity. So, and the proof only really works up to that point, up to that time. Now, so let me just introduce these two notions of weak solution for this problem. The first one, or the strongest one in a sense, is the Lagrangian solutions. And Lagrangian solutions, I basically say that a Lagrangian solution is given by a map from R2 minus the point vortex to R2. And this map is C1, and assume this map is C1 everywhere. And so that the vorticity is conserved along the trajectories of the continuous part of the vorticity is conserved along the trajectories of this map. The point vortex is evolved by the velocity given by this vorticity. And the flow map is the solution of the ODE, of the flow map equation associated to the ODE x dot equals U plus mk. And well, initial data omega naught and p naught. So this would be the Lagrangian solution, when I'm assuming this is phi is a volume preserver homeomorphism from R2 minus the point P into itself for every time. Okay. Now this would be a Lagrangian solution. Now the Lagrangian solution is something a little, it's quite a bit weaker actually. If you start with some, you're looking for a vorticity which is in L1 intersection L infinity, a point in R2, we say that this pair omega p is an Eulerian solution of the vortex wave system if omega is L infinity in time into L1 intersection L infinity, the point is bound, the trajectory is just bounded. And if we have this equation satisfied in the sense of distributions, omega t plus divergence of u plus h omega equals 0, that makes sense because I integrate par parts into the text function. And the product, u plus omega, u plus h is, say, L1 log, for instance, and omega is L infinity. So you can actually, L infinity compact subpart, so you can make sense of the product. And, well, and the OD satisfied on this integral sense. Okay? Yes?
Position is only bounded. So you're allowing the point to jump from one?
For this definition, yes. You know, of course, I'm not really allowing it to jump because I think with this kind of regularity, it's even the weak form of this equation implies that the solution is Lipschitz. Okay. But, so let me say a couple of words about the proof of Lacave-Milhaud. The main point of so this is a 2009 paper which started, let's say, the modern theory of this equation. The main point of their analysis is that when the vorticity is bounded initially constant, it will stay constant near the point vortex for all time, just like Mark Euro. Okay? So the whole point is to control the trajectory of the point vortex at the same time that you control where the vorticity is constant. The main steps of their proofs, first, they prove that Lagrangian solutions imply Eulerian, and they construct an Eulerian weak solution. Now, given an Eulerian weak solution, you show that the solutions are renormalized solution of the transport equation in the sense of the Perron-Lyons, the transport equation for omega. Now, this is well. Let me, yes. So this is a little complicated because the velocity will not satisfy the Perron-Lyons, the hypothesis of the Perron-Lyons, except that since the vorticity is constant near the point vortex, you can sort of desingularize the velocity and say, well, you can, as soon as for the transport equation, it doesn't matter what the velocity is doing near the point vortex because the vorticity is constant there. So you just...
Can you explain very briefly what means renormalized solution in the sense of
there's a precise definition of that. The renormalized solution means for any, instead of trying to show that, let me put instead of trying to show that omega is a solution of this equation here, you show that you make a cutoff of omega. And you show that the cutoff with some something that for an arbitrary, say, Lipschitz cutoff of renormalization of omega called beta of omega, that's a solution of this equation. And if you do it for an arbitrary beta, that's what it means to be renormalized. The point is that once you prove that there is a number of properties that you get out of that, including some stability from approximations. If you approximate a renormalized solution by other renormalized solutions, the limits of renormalized solution, things like that. And that's what the kind of machinery they need. So, and another issue is that if you talk about renormalized solutions, you have properties of Lagrangian maps that are uniform in parameters too. So these, and this is the whole issue for them, is to the issue is that once you renormalize solution, you have these Lagrangian maps. The Lagrangian maps are well behaved with respect to parameters. In particular, you can control how far trajectories are from each other. And this is the whole point. Then at this stage, they say there's a disk of constant vorticity around each point vortex at all times in a finite interval. They can control how big that disk gets. And then once you got that, once you get a disk of constant vorticity around each point vortex, the uniqueness and uniqueness solution is easy, and then you can actually show that it's, the solution is Lagrangian. So what they show is the existence of uniqueness of a Lagrangian solution at the end, but going through the Eulerian framework in the middle. Okay. But my point at this stage is that they bring in some fairly heavy machinery to do this. This renormalized solution theory, it's a fairly sophisticated bit of geometric measure theory that they have to bring in to do this. Now, our result is, I think, quite a bit more simple-minded in the sense the whole game in the story is uniqueness. Existence is easy. So our theorem is start with omega naught and LP, modify the continuous part, use the Mark-Yoram covariant result to get an approximate solution sequence with an uniform LP bound coming from the transport structure of the equation. Use elliptic regularity to get approximate velocity with the continuous part, which is uniformly continuous. Use Peano existence theorem, the argument, with the continuous velocities and standard. I mean, Peano's existence result is a compactness argument, so you sort of implement it, and you get existence both for the vorticity equation and for the ODE. If you have more than one point vortex, you can control the distance between vortices using the Hamiltonian. So this is basically what we do, and not very hard. And if you try to go p less than 2, the velocity is no longer p less than or equal to 2, the velocity is no longer a priori continuous. The only ODE, the theory that applies is the Perron-Lyons again. You back to that. And then the flows exist almost everywhere, so you can't propagate points. And therefore, at this stage, we don't really, I mean, at least this basic framework doesn't seem to be able to do it if you go p less, if you go p equals 2 or less. Okay. So what else have we've been trying to do at this stage? One thing that so this is an approximation. We use an approximation using modifying the initial data, and the next natural question to ask is, can you do it more physically meaningfully by approximating using the Navier-Stokes equations? So can you do a vanishing viscosity limit and recover the vortex-wave system by means of that? The truth is, okay, so this is, there is a recent result by Thierry Gallet, okay, where he proves that if you start with the Navier-Stokes equations with a finite number of point vortices, and you let it evolve using Navier-Stokes, and you send the viscosity to 0, you get the point vortex system in the limit, okay? This is a very difficult result to prove. Okay, it's at last I looked, it was a 70-page paper. And what this would be for Navier-Stokes would be a more complicated version of the same thing. It can probably be done, but it's a hard exercise just to include the continuous part of the vorticity and slog around the Navier-Stokes proof to get the convergence. So in thinking about doing that, we started a much easier problem of the same line, along the same lines, trying to justify the point vortex approximation in a more physically meaningful way. And we thought about doing it with the Euler alpha, with the Lagrangian regularized Euler equations. And I mean, the best you can say about this is that Euler alpha is just an instance of what's classically known as the blobbing methods. So it's a regularization for the Euler equations that's commonly used in numerical approximations. And it's got this nice geometric flavor to it because the solutions of Euler alpha are geodesics on a specific norm on the diffeomorphism group. So this is it gives you at least a nicer way of regularizing. So we proposed this as an initial problem with Eleonora Moura. So this is the Euler alpha in vorticity form. Just the eta is the vorticity associated to velocity, which is regularized, which is obtained from the vorticity by applying this regularized kernel k alpha. So k alpha is k convolved with the inverse of so the regularization is given by this operator here. There's nothing particularly deep about choosing this. This is just a a regularization. Okay. So global existence and uniqueness of a weak solution with an arbitrary finite measure as initial data was proven by Oliver and Scholar back in 2001. And the issue is, if I start here with data, which is the point vortices plus the exact vorticity in LP, you have a solution, then you have to pass to the limit, and the theorem is we can actually get it. We can actually pass to the limit on this equation and get the vortex wave system pretty much under the same conditions that we did with Evelyn, with mu. So here's the statement of the theorem. You start with an initial vorticity in LP compact support, put endpoints, the masses, then there exists a subsequence of weak solutions of the Euler-Alpha equation with this initial data, which converges to an Eulerian weak solution of the vortex wave system. Okay? Now, sign conditions on the vortex can be eliminated with convergence guaranteed to first collisions, the same thing. There is related work on this by Clayton Bjorland, came out in 2011, which is the convergence of the vortex blob method for the point vortex, for the vortex wave system. But again, it's a single point vortex and rather different in technique than what we're doing here. So it's the first thing we try to do with this. The next thing we try to do with this. Now, the next thing we did was a continuation of the original work with Evelyn Muir and Helena, and we tried to get. So we got the weak solution was a Lagrangian, was a Eulerian solution. That is unsatisfactory for a number of reasons. We do want the vorticity transport to be there at the limit when you have the equation, and for that you need some kind of Lagrangian version of the solutions. Now the issue is how do you construct practical trajectories for the and the flow map for this limit equation, which is an LP vorticity plus point vortices. Okay, so this is the issue. Now, what's required for this is an extension of the Dupin-Lyons-Ambrosio theory, because the vector field satisfying divergence-free curl is equal LP plus Dirac is not within their framework at all. So such a velocity, which is k convolved with omega, that's actually pretty good. Omega is LPP greater than 2, k convolved with omega is continuous. But the Dirac is, put the Dirac in, and the resulting velocity is not BV. Okay? The curl is a measure, the divergence is 0, but there are first derivatives which are not measures at all. That's actually easy to compute, to prove. So the question is, can you extend the Dupin-Lyons-Ambrosio? So this is, can you extend the Dupin-Lyons-Ambrosio sort of transport theory to something like this, given the trajectory, given a reasonable trajectory P of t? And using the fact that, sure, this is actually almost continuous, and the point is the failure is in isolated points which we control where they are. The failure of the BV norm, the BV-ness of the velocity is just at control points. And so for me to be able to do that, let me just define one bit of terminology that you use in the story, both in the Dupin-Lyons and Ambrosio theory, is the notion of a regular Lagrangian flow. And here's, so at this stage, I'm abandoning the vortex wave system. I'm really interested in just proving existence of a transport map for a velocity field, for the ODE associated to a velocity field that has this form. Okay? Basic continuous, or basically W1P velocity field plus Dirac, plus the velocity field induced by Dirac. Okay? And so let me just introduce the terminology. What's a regular Lagrangian flow? We say that a map is a regular Lagrangian flow if there exists an L2, a Lebesgue measurable. L2 is a Lebesgue measure, so it's in R2. So I want a set of zero Lebesgue measures such that for all x in R2 minus the set, the map belongs to L1 in time, the map that maps t to the velocity evaluated at the corresponding point, and x satisfies the weak form of the ODE of the flow of the ODE x dot equals b. And also I want the basically control of the measure of pullbacks. So I pick up the Lebesgue measure restricted to a ball, pull back by the flow map, and the measure cannot be too small. So the measures of balls by pullbacks is controlled. Or another way of doing this is that the measure of Borel sets to the pullback map is controlled in a uniform manner. So you can't really squeeze sets too much. So now this is what it means to be a regular Lagrangian flow at this stage. Let me just put in the hypothesis I need. I said that I want something with the conditions something of the form I want for the vortex wave system. So let me put precise conditions that I need. So B is going to be a sum of two parts, V and H. V satisfies these three conditions, the condition at infinity, V is in L1 into BV, and the divergence of V is in L1 in time into L infinity. These are the three conditions of the Ambrosio theorem. And these three conditions ensure the existence and uniqueness of a regular Lagrangian flow associated to V itself. Okay? And in addition, I need an extra hypothesis that this velocity field is L infinity in time into LQ for Q greater than 2. And this is not the vorticity. This is really, I'm saying the velocity is a bit, the smooth part of the velocity is a bit better than L2, and that's it. Okay, so that's for V. And age, I'm going to be very precise. I could actually make a class of ages for each this works, but I don't think there's any point to that. So we didn't think there was any point to doing that. So we just say that age is start with a Lipschitz trajectory Z and introduce the map K, call age of X and T is exactly K, the Biot-Savart kernel, X minus a Lipschitz trajectory Z of T. Okay? So being very precise, so the velocity that I'm working on is this general V velocity plus a very specific singular age. And age satisfies H1 and H3. It is divergence free, but doesn't satisfy H2. It's not BV log. And therefore, this is not covered by Ambrosio's theorem. But you note that age is actually smooth outside of the set T, Z of T in time. So it's a very special way of not satisfying Ambrosio's theorem. Okay? So now, here's the theorem we managed to prove, and this is brand new. In fact, I think it's yeah, there's a version of the manuscript in Archive. Okay, so this is myself, Eveline, Helena, and Gianluca Crippa added as a collaborator. Let B with the specific form, and age given as defined, and there exists a unique regular Lagrangian flow associated to this B. Moreover, for almost everywhere in Lebesgue, we have that the trajectory x of Tx does not collide with the point vortex. Now, this is not usually required on this. I mean, this is not part of the unique Lagrangian flow story, but this is really important if we want to make sense of the vortex wave solution that we have. Now, the proof comes with an explicit construction of the approximate Lagrangian trajectories on an error estimate. This follows the explicit construction follows ideas that were used by Lacavemille, the approximation scheme that was used by Lacavemille in their paper, and another and sort of limiting stability ideas by Delelis and Crippa, paper by Delelis and Crippa on the same story. Okay. So the yes.
So Z is the position of the point vortex?
Yes, Z is the position. At this stage, there is no point vortex. I'm just talking about a linear transport equation. But Z is indeed the center of the H part, the singular part of the transporting flow, of the transporting vector field. Okay. At any rate, so this is the. With this result, together with our theorem, now we get a Lagrangian solution of the vortex wave system, but in a weaker sense than what I did write down what the definition of a Lagrangian solution was here, And what we get is a Lagrangian solution, but in a sense that's weaker than this. Okay, and so there's a now almost everywhere sort of game playing around here, except that even with this almost everywhere game, I can still say that the point vortex is a Lipschitz trajectory that's associated to this story. Now, so let me. So this is what we proved so far. So let me just tell you a few things beyond this. Okay, this is what we know, and it's everything. So everything that's known about this system, I already told you. So let me just say a couple. So you shouldn't expect weak uniqueness for the vortex wave system with vorticity in LP, because the velocity in this case is C1 alpha for alpha less than 1, and no better than that, in fact. And standard non-uniqueness examples for ODEs come to mind. So at this stage, it would be very surprising that you get anything like uniqueness for the vortex wave system in a situation where the velocity is really not Lipschitz. Okay? But for p equals infinity, and this is now the Udovich case, it is not unreasonable to expect uniqueness. Now, this is an important issue. Okay? So let me. So the whole issue is this is a linear. So the vortex wave system, in some sense, is a linear perturbation of the vorticity equation. Of course, if you start with an initial vorticity which is L infinity, this vector field here U is basically log Lipschitz. And you do have uniqueness for the transport equation the nonlinear transport equation in this class. And you even have a little bit of space left. You can actually have the vorticity be slightly unbounded and you still get uniqueness. Now, if you strike out the U, or if you look at just as a linear equation and forget that U is coupled with omega, and you let this thing evolve, I just proved that you have uniqueness for the solution of the transport equation by itself, the linear transport equation. So it makes a great deal of sense to think that, okay, so if the initial vorticity is L infinity, this thing should have a unique solution, but I don't know how to prove it. Okay? So when p equals infinity, it's not unreasonable to expect uniqueness. We do know uniqueness if the initial vorticity is constant near the point vortex. But we don't know if the initial vorticity is variable near the initial point vortex. Okay. Now, it would be very nice to remove this last assumption, give you a complete result that would be a really nice extension of Udovich's original result. Now, there's two things I want to say about this. First, there is fairly serious physical motivation for looking for this uniqueness. Okay, it doesn't matter that the background vorticity is just infinity. It doesn't matter. I can make it C infinity. Just think of it as you know, I want the point vortex to live on a background vorticity that's smoothly varying. These are numerical studies done back in 2001 on a paper by these two guys, Schechter and Dubin, came out in Physics of Fluids. And they were simulating point vortices on a varying vorticity background. So it's precisely the situation I've been talking about. And now you can see what happens. I mean, they put 2 point vortices in different signs. And of course, since the vorticity is varying, the point vortices act as a kind of a blender, a very dramatic blender, and create a big mess where the point vortices are. And then this big mess evolves and gets complicated. And here is, again, a background which is smoothly varying, and the interaction of the vortices with the background make things move around and create, and this is the whole issue that I want to point out with these pictures, it creates a lot of small scales. So the point is, if the vorticity is constant near the point vortex, the whole thing, the whole motion is fairly smooth. There's nothing going on there. Even though the point vortex is dramatically irregular, the constant vorticity background means there's nothing to know that this big drama is going there. But as soon as you put some kind of varying vorticity background, the point vortex will generate a lot of small scales, which is what you'd have to control if you want to actually close the story and prove the uniqueness for this problem. Another issue is this is the point vortices, the 2D point vortices with a vorticity background is a very natural rough model in geophysics, and that's the reason why I chose to give this talk in this particular context. Now, people have used point vortices as a rough model for storms storms in the atmosphere, and of course the rotation of the Earth. If you look at it in vorticity term, it's a source term. So even if you start with initial vorticity, which is 0, at the scale of hurricanes, for instance, the rotation of the Earth produces a background vorticity field which is smooth and non-constant, depending on latitude. So this is a very natural question to ask at that context, especially if you can recast the whole story that I'm telling you on a rotating sphere. The story is basically the same, except that then you cannot put the hypothesis that the vorticity is constant near the point vortex because it doesn't stay that way. So this is what makes this problem interesting, and we're still working on it to some extent. But as I said, it's pretty hard. So the open problems so just as a conclusion, just to conclude my talk and give you some directions that we are playing with. So the first thing is to just recast this whole story in the surface of rotating sphere is a rather natural issue. We've been playing around with this. It's a bit of an exercise, not terribly deep. There is one problem. In fact, it's what started this whole story is this problem of the stuck vortex, which is we've started playing around with the limiting behavior to the ideal flow in the exterior of a small obstacle. And if if you have circulation around the small obstacle, when you send the obstacle to 0, you end up with a point vortex. But this point vortex, instead of moving around with the flow, is just stuck there. So you end up with a point vortex at the origin. And the same set of estimates and ideas that do the vortex-wave system, it can actually be used for this limiting problem of the ideal flow on the exterior of a small obstacle. And the uniqueness question is the same, and this whole issue of uniqueness would have to do with turning a compactness result, which is what we proved with IFTME back in 2003, into an actual convergence result and doing error estimates. So this would need this uniqueness story, and Lacaze and Miot actually proved uniqueness if the vorticity is constant near the stuck vortex, and they actually proved that if you start with it constant near the stuck vortex, you'll stay that way forever, which is a somewhat counterintuitive result but this is part of their work, Lacaze and Miot. And so at this stage, this would be, this is, as I said, this is a related problem that one can actually go, by now you can actually go in there and try to do error estimates because you have Lacaze and Miot's result. One issue that we would really be interested in is what happens if you put points. So this is a situation where you don't have a velocity a priori continuous, but if you have a vortex sheet and a point vortex, at least initially you have analytic velocities playing around with one another, and makes sense to study a little bit what happens with the interaction between point vortices and vortex sheets. So this is an issue to be thought about. And something I mentioned during the talk is the vanishing viscosity limit, an extension of the work with Eleonora Moura on the alpha Euler. Okay, so now we did it for the alpha Euler. Let's tool up and do the vanishing viscosity case, which we've been sort of trying to gather courage to actually do. And well, I think that's it. Thank you.
Okay, thank you very much for a very fascinating talk. Are there questions?
You have tried to have larger and larger classes of hypotheses for which you have uniqueness. What happens actually if you don't have uniqueness? And what does it mean?
Oh.
For instance, you discuss the physical implication through this computation of the bin and check there.
Sure. The physical issue is if you don't have uniqueness, what you have is a defective model, right? You cannot use it to predict what's going to happen, and then you have more than one way of dealing with that situation, right?
So it means basically that if you regularize your initial condition, and you should expect to have a different solution
You may-
depending on the way you regularize it.
for instance.
That's what,
Yes. It's easy to produce examples of that for these, where situations so simple you can actually do calculations. And it's very conceivable that the situation is the same here. One question that I asked, what we've been sort of playing with, you have these collisional vortices, right? You have the three vortices that collide in finite time in one point. And if you look at Oliver and Scholar's result, if you put the three vortices there for alpha Euler, you have a solution for all time. But in our scheme here, you only have convergence up until the time of collision. So it's fair to ask, what happens afterwards? Do we lose this kind of prediction ability in this approximation? I mean, we don't know what we don't actually know what the Oliver and Scholar what the Oliver Scholar example. How does that work with the colliding point forces example? I know they don't collide. But maybe they get close and they stay close forever. Maybe they get close and they separate. We don't know. And it'd be an interesting question too. But I mean, this kind of thing, the collision. I think this has been explored for the n-body problem. You have two bodies collide; they are nearly particles, and of course, then they have non-uniqueness in the sense that you can't really predict what's going to happen after collision with a particle model. I guess that's the point at this stage. Maybe the particle model just doesn't work.
Going back to this, in some other context, there was an idea to consider weak solutions with time integration as well as space integration, to include those colliding vortices. Not for Euler, but for some other models. So were there any, are you aware of any such attempts?
That's what I think that's what we're trying to do for going down to vortex sheet. It's something we didn't. I don't think the result is. We have some kind of proof, but it's not correct right at this stage. We have a wrong proof of that. Using exactly this idea, but bringing it down from p. So use the time integration to bring things down from p greater than 2 to more irregular flows. But I didn't say anything because we haven't gotten there yet in any way.
So in your reconstruction of the Lagrangian flow, you seem to not be able to exclude that a certain small set of trajectories is actually crashing into the singularity.
But it's a measure zero set.
So do you think that's an intrinsic feature of the problem, or is it just a technicality that it's hard to prove that?
No, I think this is for this level of work. It's not a technicality. It's the real thing. You can have a measure zero set of trajectories crashing into the particle, but not more than that. The point is that doesn't. The whole question is, can the mass of the point vortex vary with time? And what that kind of Lagrangian definition does, the kind of definition Lagrangian does, is say no, you cannot exchange vorticity with the background. And this is the key issue at this stage. But I don't think with a LP vorticity you get. You essentially not going to get anything better than almost everywhere information out of the ODE theory. I think in some essential way.
More questions? So let's thank Milton again.